What's up, ladies and gentlemen? Today we're going to be talking about the cardiorespiratory system. Let's get it popping. So the cardiorespiratory system is composed of kind of two different parts there. We'll first start with the cardiovascular system. And the cardiovascular system, okay, as you can see by this diagram here, is made up of your heart, okay, and all the blood vessels that travel throughout your body. We'll talk about these a little bit more in the coming slides. So blood vessels here, okay, are different kind of canals or passageways that blood travels throughout your body, okay? And from the heart there, we start with your arteries, okay? And arteries are specifically blood vessels that carry blood away from your heart to the rest of your body. And majority of the time there, they're typically carrying oxygen-rich blood, meaning a lot of oxygen is transported by your arteries. However, this is not always the case. For example, pulmonary arteries, they take oxygen-poor blood and transfer it from your heart to your lungs. So arteries, simple as it can be there, carries blood away from your heart. Roughly 10 to 15% of your blood is in your arteries at any given time. Now, as the blood gets further and further away from your heart, arteries become arterioles. Essentially, arterioles are kind of smaller arteries in a sense there. And then finally, we get to the smallest type of blood vessels, which are your capillaries. Okay? And this is where gases and nutrients are exchanged at different tissues, at organs, okay? Things along those lines. Then coming back to the heart there, we got venules. Okay? Venules are a little bit bigger than capillaries. Okay? And venules then transform into veins. Veins are the largest blood vessels taking blood back to your heart. And usually, veins are going to be the opposite of arteries there in that they have very low oxygenated blood. So very little oxygen is typically found in the blood in your veins there. However, okay, the one exception there are pulmonary veins. They carry oxygen-rich blood from your lungs to your heart. And roughly 75% of your blood at all times is in your veins. Here's the rule for arteries and veins. Arteries carry blood from the heart, while veins carry blood to the heart. Again, oftentimes arteries have oxygen-rich blood versus veins have oxygen-poor blood, but this is not necessarily always the case, as shown as examples in the previous couple slides. Now here is, if you follow this path here, you can follow the path of the blood here, okay, through your heart, your arteries, your veins, okay, throughout your body there. We are just going to focus mainly on the right atrium, right ventricle, left atrium, and left ventricle in this PowerPoint slide set. So if you take a look at your heart here, the top two chambers, okay, are called atria. Atria is plural for atrium. One of these top chambers there would be considered an atrium. Okay, and these atria there, they receive blood coming from the body, whether it's coming from your lungs or from your arms and legs and head, things along those lines. Now, the atria will pump the blood into your ventricles. Your ventricles are your bottom two chambers of your heart there, and these are larger chambers. Okay, and the reason these are larger is these two larger chambers, when the heart contracts, pushes blood throughout the body, whether again it's to your lungs or to your head, your arms, your legs, things along those lines. But this gives you a visual representation where the atria are and where the ventricles are. Now, as we've discussed previously, because we're dealing with the heart there, cardiac output is going to be very important. Cardiac output there, represented by the letter Q, is the volume of blood that a heart pumps each minute. You can find that by multiplying your stroke volume, or how much blood is pumped with each stroke. Multiply that by a heart rate there, which is the number of times that your heart contracts every minute. Now here's also something very interesting, okay, about your cardiovascular system. Okay? Your blood vessels will vasoconstrict and vasodilate depending on the particular situation. What vasoconstriction is talking about, constriction, think of kind of like a boa constrictor wrapping around you and squeezing you tight. So vasoconstriction means blood vessels get thinner. okay? And specifically, okay, the areas of the body that are not as active, okay, meaning they don't need as much oxygen, okay, those blood vessels will constrict during exercise. So, for example, if I'm performing a back squat, okay, the blood vessels in my arms will probably vasoconstrict because the blood needs to go to my legs when performing a back squat, okay, not necessarily as much to my arms, okay. Also, vasoconstriction will occur to blood vessels that go to your different organs. For example, your stomach is very important. It needs to be able to digest food. However, during exercise, digesting food is not important. What's more important is getting blood to the working muscles. So therefore, the blood vessels that go to your organs, such as your stomach there, will vasoconstrict during exercise. Now, on the opposite side, vasodilation means the blood vessels get bigger, and these blood vessels are going towards the working muscles when you exercise. So again, using that back squat example, okay, my leg muscles need a lot of blood there in order to squat that weight up and down there. So therefore, the blood vessels in my legs will vasodilate and get bigger. Therefore, more blood can get to those working muscles there. Vasodilation, the way I like to think about it here is if your pupils are dilated, that means your pupils are larger. Okay, so vasodilation means your blood vessels get wider. Here's a visual graphical representation of where blood typically flows at rest compared to exercise. So it's important to notice here how there's a good chunk of blood going to a lot of different areas of the blood at rest. To the liver, to the kidneys, okay, your brain, muscles, heart, things along those lines. However, during exercise, you can see the vast majority of the blood there goes to your working muscles there. And to your other organs there, very little blood goes to those areas. Because again, those are the areas of your body that needs the blood immediately there. Here's another visual representation here. Okay, what this is looking at is the intensity of exercise, okay, represented oftentimes by the amount of oxygen, okay, that's consumed by your body. As the amount of oxygen increases, okay, which means that you're working harder, the amount of blood going to your skeletal muscles that are working starts to increase, okay, go up and up and up, and the blood flow to your other organs there will start to decrease as the intensity of exercise increases. Here's another visual representation, but this visual representation looks at differences between your arteries, your veins, and your capillaries, and where blood flow and other variables, how they change there as the blood travels throughout your body. Okay. So on the left here, okay, your aorta is one of your biggest arteries, okay, and then you got your other arteries as well here. But what you'll notice here, okay, is that blood flow is very high coming from your heart, and that would make sense going into your arteries. Okay, so but blood is pumped out by your heart there, pushes that blood throughout your body. So the velocity of your blood flow will be very high coming from the heart. Now you'll notice here as we get closer and closer to your capillaries, okay, which specifically is highlighted here in purple, okay, the blood flow velocity will decrease immensely, okay? So blood flow slows down, okay? Now why does it slow down here? Okay? A couple of reasons there. Number one, let's take a look at the total vascular area, essentially how much blood is in your blood vessels at this particular given time. And what you'll notice here is capillaries have a lot more or contain a lot more blood there compared to your arteries. So just like, okay, if water's rushing down a river, okay, and gets to this lake here, emptying out into a lake there, the blood flow is going to be faster in the river, okay, and then when it gets to the lake there, the flow of water will slow down because there's a lot larger area for that blood to go. So likewise, since there's a lot more volume of blood that is in the capillaries compared to the arteries, blood flow will slow down there, okay, when it gets to the capillaries. Okay. In addition, okay, partially because of this, because there's a lot more area for blood to travel through when it's in the capillaries there, blood pressure will decrease. So blood pressure is high there, okay, in the arteries because that's just where the heart has pushed that blood, okay? And since the heart just pumped the blood there, the blood is flowing the fastest, okay? But again, partially due to the larger amount of volume that is contained in the capillaries, okay? That's another reason why the blood's slowing down there, therefore there's less blood pressure, okay, in the capillaries. Now, let's take a look at the veins. What happens to the veins? What you'll notice here is blood flow velocity actually increases, okay, when we get to their veins. That's weird. Why does it start to increase, okay, when blood gets to the veins? Okay. Number one reason is the vascular area there, okay, becomes a lot less. So as we get to our veins here, the total amount of blood in those veins is a lot less compared to your capillaries. So with a smaller area there, okay, the blood is kind of like, I guess, kind of trying to force its way, cram its way into these more narrow tunnels. However, another reason is what we'll talk about in the next couple slides. There are different mechanisms that help speed up the blood flow in your veins. And here are a few different things there that assist with the blood getting back up to your heart. And one reason why, okay, blood flow velocity actually increases in your veins compared to your capillaries. Okay. Number one is the muscle pump. So literally by your muscles, your working muscles contracting, okay, and relaxing, they squeeze that blood in your veins, helping push it back to the heart. Secondly is the respiratory pump, okay? And we'll talk about this a little bit later on in this PowerPoint slide set, but essentially there's less pressure, okay, around your lungs there, okay? So therefore, the blood wants to go from an area of higher pressure, which is in your limbs, to an area of lower pressure, which is towards your lungs there. So therefore, the blood will actually will speed up there, trying to get to that area of lower pressure, closer to your lungs and your heart. Yeah. Thirdly, though, is venoconstriction. So your veins literally have muscles around them, and they squeeze and contract there, helping push more blood there back to the heart. So these three different mechanisms there help assist with increasing the velocity of blood flow as it gets back to the heart there, okay? Assisting with venous return. Here's a diagram there of kind of what that's looking at. Okay, so number one here is the muscle pump. So as your muscles squeeze together, okay, they push that blood towards the heart there. Okay, we've got in letter D here, we got venoconstriction. One thing I like to point out, veno, okay, we had vasoconstriction before. Vaso, just talking about blood vessels, but veno specifically talking about veins. But constriction there again, squeezing together. But we got muscles around your veins there that squeeze to help assist with blood flow going back to the heart. A third unique structure in the veins, though, is that unlike arteries, veins have valves. And these valves here will close up between heartbeats, okay? And this helps then prevent a backflow of blood in your veins. So with these valves closing, okay, that helps prevent blood from going the opposite way in the body. Moving on here, okay, so we just talked about a lot of different characteristics of your blood vessels. Let's talk about cardiac muscle. Now, unlike muscles in virtually the rest of the part of your body, things like muscles in your arms and your legs and your torso, okay, cardiac muscle has some factors, some that is unique to cardiac muscle and some that it shares with the other muscle in your body. Okay, one thing that is a characteristic of cardiac muscle is that it is excitable. Okay, meaning that we can zap cardiac muscle and cause it to contract. Okay, so if you took out a piece of heart tissue and you put an electrode on it and send send electricity into that heart muscle there, that heart muscle would contract. Okay, so cardiac muscle is excitable. Okay, and this is common with all different muscles. So this is a characteristic that cardiac muscle shares with other muscles in the body. However, what's unique to cardiac muscle compared to muscles in the rest of your body is that cardiac muscle has an inherent rhythmicity to it. Okay, meaning that just the rhythm of the heartbeat there can excite okay, different parts there of the muscle. So by rhythmically contracting, okay, cardiac muscle that is unique to cardiac muscle versus muscles in your arms and legs do not contract rhythmically. Thirdly, okay, cardiac muscle has characteristic of conductivity, okay, meaning that adjacent cells can take the excited heart muscle cells there, okay, and the adjacent cells being excited there or have an electrical stimulation that can cause the other next door cardiac muscle to contract there, okay, and that is unique there compared to normal muscle in the body. Okay? And then, just like with normal muscles in the body, cardiac muscle are able to contract. So essentially, okay, these two middle characteristics are unique to cardiac muscle versus excitability there and contractility. Both cardiac muscle and normal muscle share these two different factors. Now, we talked about how cardiac muscle can be electrically stimulated, and we talked about how it can be rhythmically stimulated, and we talked about how the excitability of surrounding muscle fibers in the heart there can be passed on to the following muscle fibers. And this is kind of the electrical path, okay, that electricity flows through the heart, causing it to contract, okay. So, bunch of different parts of the heart, and I'm not going to need you to be able to pick these out of thin air there on a test question, but I do want you to be familiar with these terms here. So first of all, when electrical signal gets to the heart there, it starts at the SA node. That is abbreviation for sinoatrial node, and that's in the top right corner of the heart there. This is a front view of the heart, so pretending this is your own heart, SA node is in the top right corner. Now, electrical signal, okay, once it gets to the SA node, it will go down these internodal tracks, essentially these kind of highways, I like to think about it there. From there, the electrical signal will get to the atria, okay, so the top two chambers of the heart. Electrical signal further goes down, and in the middle there, we've got the atrioventricular node, otherwise known as the AV node, okay? And past the AV node there, we've got the AV bundle, okay, otherwise known as the bundle of His, okay? From there, electrical signal goes down the right and left bundle branches, okay, of the heart there, okay? Travels all the way down to the Purkinje system. Essentially, Purkinje system there is these little kind of looks like little bumps here, okay, that are connected to the valves of the heart, okay, and then the electrical signal goes throughout the rest of the ventricles there. So it's important to understand the path that this electrical signal will go through the heart there, okay, but I don't need you to pull these different parts of the conduction system out of thin air. Now, how do we measure the electrical signal in our heart? Okay, we do this using different pieces of medical equipment, but this essentially pattern there of electrical signal, okay, shows typically the electrical signal traveling through the heart with each beat. Okay, from P through U there is example of one heart contraction. Okay, and then P to U here would be a second heart contraction. And essentially, this repeats over and over again if people like medical professionals, okay, things along those lines, are measuring the electrical activity of the heart. And based off of these different parts there of the electrical signal, we know where at the electrical signal is passing through in the heart there. So essentially, which parts is the electrical signal at there when the heart is contracting. These next few slides I would definitely make a note of somewhere, okay? I would write down this information, okay, to understand the electrical signal as it passes through the heart, okay? First of all, the firing of the sinoatrial node, that SA node there, all the way in the top left corner there, okay, that is represented by the P wave. So where the P wave is at, that's where the SA node fires. Also during the P wave there, okay, there's a depolarization and contraction of the atria. So depolarization, okay, essentially, not to go too fancy into things there, but essentially their depolarization, okay, talks about how in heart muscle or in any sort of muscle tissue, okay, muscle tissue is inherently has a negative charge, okay. Um, when a muscle contracts, though, okay, that negative charge all of a sudden becomes positive, okay, and that positive change in the electrical signal there causes that muscle there to contract. Again, I'm not going to go into fancy details about it, but just understand at the P wave, not only do we have the firing of the SA node, we have the depolarization and contraction of the atria. So essentially the atria are squeezing during the P wave. Now at the atrioventricular node in the middle here, there's a delay. Okay? And this delay is represented by the PR segment. So from here to here, okay, this represents where the electrical signal is essentially paused or halted for a second or for a moment, okay, right here at that AV node. And one of the reasons it does that there is it allows electrical signal to get further around the heart and the other tissues. Now, the big segment here, okay, the QRS complex, okay, where there's a big spike, okay. As I mentioned previously, in the P wave there, okay, there's a depolarization, meaning the heart goes from negative, okay, to either slightly less negative or a little bit positive, okay. But during the QRS complex, the electrical signal goes extremely positive, okay, and then it jumps right back down, okay. So essentially, the ventricles become extremely positively charged, okay, and they contract there during the QRS complex. As this is happening, so as the ventricles are contracting, okay, there's a repolarization of the atria. Okay? Repolarization meaning the atria go from positively charged or a little bit less negatively charged to more negatively charged. So even further negative value there during the repolarization of the atria. So during the QRX complex, this represents electrical signal that's happening through the ventricles. However, at the same time here, which is disguised there, the atria there are repolarizing. Then during the T wave and sometimes the U wave, if it's highlighted there in certain people there, the ventricles repolarize. So essentially, the ventricles are relaxing there, and the ventricles are going from being positively charged to being negatively charged. And this slide here kind of highlights, if you wanted to exactly see where in the PQRS, T, and possibly U phases there of the electrical signal, where is that exactly at the heart? So for example, in blue here, okay, that's where the electrical signal is during the first half of the P wave. Again, this is for your own benefit if it helps you visualize things, okay? But I'm not going to test you on this particular slide here. But this stuff, okay, understanding this, and this here would be something that I would make a note of. Now, one of our life-saving measures that we have, okay, when somebody goes down, there is a defibrillation tool there, okay? So an automated external defibrillator, oftentimes abbreviated as AED device, okay, can be used to help people who are having heart issues, okay? What an AED device can do, okay, is important to note is that it can help get a heart back into rhythm, okay? Meaning that the heart sometimes goes out of rhythm, okay? We call a heart that's going out of rhythm there, we consider that an arrhythmia, okay? So an arrhythmia means that the heart is not beating properly, okay? Fibrillation there, okay, means that we just have, there's various different arrhythmias that can happen in the heart there, okay? Now, what this AED device does is it helps to get this irregular heartbeat back on track, and it does it by shocking the heart there when it detects an electrical signal there and when the heart is ready to be shocked there. Now, however, what's important to note here, though, an AED device will not restart a heart that has ceased beating. So essentially, if a heart does not have any electrical signal, an AED device will not help. There's got to be an electrical signal in the heart, okay, for the AED device to help out. But if someone's dead and has no more electrical signal going to that heart there, it cannot jumpstart them again. So we just got done talking about the cardiovascular system of your cardiorespiratory system, talking about the hearts and your blood vessels. Now we're moving on though, okay, because we want to talk about the pulmonary system. Pulmonary, think of lungs there, okay? Because one of the reasons we need to pump blood throughout the body there is we need to deliver oxygen to where it needs to go and get rid of carbon dioxide. So the pulmonary system, okay, is important there in the body, and we're going to talk about it in the next several slides there. Okay? Pulmonary ventilation is oftentimes two synonymous terms there, because ventilation, we think of breathing there. Pulmonary, think of lungs. Now, we're going to go through a couple different terms here that go with ventilation and breathing. Minute ventilation, some people call it minute ventilation, is the amount of air or volume of air that we breathe in or the amount of air that we breathe out there every minute. So every time I breathe in, number of times I breathe in each minute there, the total amount of those breaths in there, the amount of air that we breathe in, that would be in 1 minute, would be considered minute ventilation. Tidal volume, okay, specifically, is the volume of air we breathe in or the amount of air we breathe out with each breath. So if I go, that total amount of air breathing in there would be an example, or would be the volume of air we breathe in with each breath. So that would be an example of tidal volume. Frequency is the number of inspirations or the number of expirations we make every minute. So essentially, tidal volume, or the total amount of air we breathe in with one breath, multiply that by frequency, number of breaths we have in a minute there, that will multiply together will give us minute volume. Now, at rest there, okay, your minute ventilation, okay, total amount of air we breathe in and out every minute is going to be roughly 4 to 15 liters per minute, depending on the size of the person, amongst other factors. Typically, the bigger the person is, okay, the higher their minute ventilation is going to be. And that would make sense. Bigger people have bigger lungs. Not only that, they typically have larger organs, typically have more muscle, and so therefore they need to get oxygen to those muscles and larger organs, and we need more of that oxygen. Tidal volume, okay, at rest there is going to be typically 400 to 600 milliliters for every breath. And typically someone's going to breathe in 10 to 25 breaths for every minute. Now, contrast that during exercise. During exercise, what happens to breathing? No crap, Sherlock. We breathe faster and we breathe deeper. Okay? So minute ventilation may exceed 180 liters per minute in men and 130 liters per minute in women. And again, that would make sense. Men are typically larger, so their lungs are going to be bigger. They typically have larger organs and typically have more muscle. Therefore, they're going to have deeper breaths in every minute there compared to women. All right, so here's two different graphs here. Okay? And these two graphs have a few different things I want you to take a look at. First of all, on the left side, the y-axis, okay, VE represents ventilation, okay? And essentially looking at minute ventilation. So again, total amount of air we breathe in or the total amount of air we breathe out every minute there. On the bottom here, we have VO2, or VO2 on the left side, I should say. Some volume of oxygen being breathed in with every breath, okay? And on the right side here is VCO2, or the amount of carbon dioxide we expel every minute. A couple things that I want to point out here, okay? First of all, let's take a look at the difference between untrained and trained people. What you'll notice is at rest, okay, the amount of oxygen breathed in every minute, the amount of carbon dioxide being expelled every minute at rest between untrained and trained is going to be the same. And that would make sense. At rest, your muscles aren't working, so you only need a set amount of oxygen to breathe in or a set amount of carbon dioxide to breathe out there every minute. As we start to, let's take a look on the left side here. As the intensity of exercise increases, VO2 is going to increase, and that would make sense there. Okay. Likewise, on the right side here, at the faster we exercise, okay, or the more intensely we exercise, the amount of carbon dioxide we produce is going to increase, and that would make sense again. What you'll notice, though, is that comparing an untrained runner, aerobically trained runner, to a trained aerobically runner, the amount of oxygen, okay, being consumed is going to be less in the trained runner compared to the untrained runner when running at the same speed. Okay, so for example here, if we're running at, let's say 100%, the fastest speed that an aerobic runner can run at there when that runner is untrained versus a trained runner, that untrained runner is going to breathe a lot more. Okay, look on the left side here, going to breathe a lot more air in and out, okay, compared to the trained runner. And that should make sense because that aerobically trained runner, okay, is better able to more efficiently use their body to exercise. And so therefore, they're not going to need to consume as much oxygen because they are more efficient with the oxygen that they actually consume. Now, if we move on there, okay, not only at slower speeds can a aerobically trained runner, okay, breathe less than a untrained runner, but that trained runner can ultimately, at the very end there, okay, when they reach their maximal aerobic speed, they can actually breathe more air in, okay, at their max compared to the untrained runner can breathe in at their max. And that would make sense there. Looking at the right side here, okay, similar things are seen with carbon dioxide. So at slower speeds, we'll notice that the aerobically trained runner produces, they produce less carbon dioxide, okay? So therefore they don't need to breathe in and out, okay, as quickly as that untrained runner, okay? And not only that there, okay, the trained runner, when training at maximal speeds versus the untrained runner training at maximal speeds, that trained runner can produce more carbon dioxide, okay, comparing their maxes there compared to that untrained runner's max. And that would make sense because that person's able to utilize that carbon dioxide efficiently and can more efficiently get that carbon dioxide out compared to that untrained runner. So make a note on this slide here that you understand the difference between a trained runner versus an untrained runner when it comes to the amount of oxygen being consumed, amount of carbon dioxide being expelled, okay, how it compares to submax versus maximal exercise, and how this relates to breathing. Now, what's also important to note here, though, is looking at amount of oxygen being consumed versus the amount of carbon dioxide being expelled there as the intensity of exercise increases. Okay. What happens with oxygen is that at the beginning, there's roughly a linear relationship between the amount of oxygen being consumed and the amount of breathing that's occurring. Okay? Meaning that as we gradually increase the speed of exercise, okay, the amount of breathing in and out that will happen will increase by a steady amount. However, okay, we get to a point there where the amount of breathing compared to the amount of oxygen being consumed will spike up, meaning our breathing, amount of air we breathe in and out, will increase a lot more rapidly as we get close to our max, okay, compared to the amount of oxygen we're actually consuming. So essentially, we're breathing more air in and out there, okay, but we're not using as much oxygen as we, I guess, would like to, or at least compared to at slower speeds. So there's essentially a curved linear relationship as we get closer to our max with the amount of oxygen being consumed there. Now take a look at carbon dioxide. Carbon dioxide will maintain at steady pace. It will have a linear relationship, meaning that there's going to be a proportional increase in the amount of oxygen being expelled, the amount of breathing that happens when we look at rest, at submax speeds, and at maximal speeds. So essentially, there's a steady relationship between carbon dioxide being expelled and your breathing rate. The amount of ventilation that's happening. One last thing that's very important to note there is that ventilation, okay, is controlled more by the need to eliminate carbon dioxide, not by the need to obtain oxygen. So if you hear the phrase there, people says, oh, when I'm running faster there, I need to breathe more often and breathe in deeper because I need to get more oxygen to my working muscles. And that's technically not right. What's technically correct is I need to breathe in and out faster and breathe more in and air in and out faster because I need to get rid of that carbon dioxide that's building up there in my bloodstream. So control of ventilation is controlled by the amount of carbon dioxide in your body and getting rid of it compared to oxygen. Now, how does ventilation change across an exercise bout there? Right before an exercise bout is going to happen, typically ventilation will increase, meaning you start to breathe a little bit more frequently. Your breaths might be a little bit deeper in nature. And that's due to anticipating the exercise bout that's going on, or that's about to happen. So as a mile runner, okay, gets up to the starting line just before their race there, their ventilation will elevate a little bit, okay, due to getting ready and being prepared for their race. As person starts to run and exercise there, there's going to be a rapid increase due to your limbs starting to move. As your limbs start to move there, okay, those limbs moving there is going to start to accumulate a little bit of carbon dioxide, or is going to start accumulating some of that lactic acid in your muscle. And your muscle then needs to get rid of that lactic acid there, okay, essentially converting it to carbon dioxide, and then we breathe that carbon dioxide out. So essentially, as lactic acid starts to build up, okay, carbon dioxide levels will rise in your muscles or in your bloodstream there, and therefore your body's got to get rid of that carbon dioxide, so breathing rate will start to increase. Now, as we get closer and closer to our body reaching a steady state pace there, for example, of running a 6-minute mile, as I start running at that 6-minute mile pace, as my aerobic energy system has been kicking into higher and higher gears, they're getting ready to maintain that pace there. There will be a slower increase. So we got a rapid initially, and then a slower increase, okay? And this slower increase happens due to the balance of creating carbon dioxide and eliminating it. Essentially, getting those carbon dioxide levels more, level there in your bloodstream. Now, once the exercise bout has stopped, so you've stopped running, okay, there's going to be a rapid decrease, okay, initially due to your limbs stopping moving. As your limbs stop moving, okay, therefore, lactic acid is not being, it's essentially not going to accumulate as quickly. There's a little bit of accumulation upon initially stopping the muscles contracting, but it won't make things, any worse and worse in the long run there. So eventually the lactic acid levels will start to level out, okay? But that rapid decrease is due to your limbs stopping to move, okay? And then as we continue to get rid of that lactic acid there, and we start to get rid of more and more of carbon dioxide levels or production will decrease, and therefore causing your ventilation there to slow down. So we've seen this slide before here, okay, in previous chapters there, but I'll highlight here the different parts we just talked about in the previous slide. So just before the exercise bout begins, okay, so from here to here, just before the yellow part, ventilation will increase a little bit. Again, that's due to you anticipating exercise. As we start to move our limbs and start our exercise bout, it's going to be a rapid increase, okay, followed by a slower increase. If we reach a steady state pace, okay, where we kind of level off there the amount of oxygen we're bringing in and amount of carbon dioxide we're expelling, okay, this is where carbon dioxide levels during some max exercises will kind of level off there in your bloodstream. Okay. Upon stopping exercise, our limbs stop moving, causing a sharp decrease in ventilation, but your breathing maintains at an elevated rate there, long past that short drop in breathing. And that's due to your body gradually getting carbon dioxide levels back to resting levels in your body. During maximal exercise, we see similar things, okay, except there's going to be a more dramatic rise in that ventilation before the exercise bout begins. Okay, a steeper increase. Okay, and during maximal exercise, we never actually level off there. Carbon dioxide levels continue to rise and rise and rise in our blood until eventually we can't maintain that pace anymore. Okay, we got to stop, causing that sharp decrease in breathing initially, and then a slowing off of the pace after that. Now, what's happening in our lungs there as we breathe the air in and out? Okay, what's important to note about that there is that in your lungs there, okay, we've essentially got these tree branches that are going down into your lungs there, okay, and these different air passageways, okay, we've got what's considered a conduction zone, and we've got a transitional and respiratory zone, okay. The conduction zone, okay, is considered the anatomical dead space, okay, and these are like tree branches, hollow tree branches in your lungs there, where air passes, okay, from your mouth there, okay, traveling down into your lungs. But in this anatomical dead space there, oxygen, carbon dioxide cannot be exchanged, meaning we cannot absorb oxygen in this anatomical dead space, and we cannot get rid of carbon dioxide in this alveolar dead space there, or in this anatomical dead space. Okay? The only place where we can exchange oxygen and carbon dioxide is in our alveoli, okay? And the alveoli are the ends of your tree branches, okay? And at these ends of these tree branches there are these sacs, okay? Little balls there at the end of your tree branches. And so the end of the tree branches where the alveoli lie, this is where we can absorb oxygen and get rid of carbon dioxide there. So we need to breathe enough volume in, so our tidal volume must be large enough there to get past this alveolar or this dead space here, anatomical dead space, so that the gases actually get to the alveoli there in the bottom parts of these tree branches. Here's another view here of the alveoli. Okay, so what you'll notice about the alveoli, okay, these sacs there at the ends of your tree branches, okay, a bunch of different balls there. What you'll notice here is we got these arteries and veins there that are spiderwebbing or essentially surrounding these alveolar sacs. And that's important because the more blood vessels we can get surrounding these sacs, okay, the more oxygen can be taken up by the bloodstream from the air, from our lungs there into the bloodstream. And we can get rid of carbon dioxide from the bloodstream into the airspace in their alveoli so we can breathe out that carbon dioxide. Another interesting fact there, okay, if you were to take one of your lungs there, the amount of surface area in those lungs there, okay, in those alveoli, okay, and the different branches, those different essentially tunnels there in your lungs, if you were to spread out all that surface area would be enough to cover essentially half of a tennis court. So even though it seems like not a whole lot there, there's a ton of surface area in your lungs there to allow for the exchange of carbon dioxide and oxygen. Now, with your breaths in and out there, we can measure, okay, different lung volumes, okay? So essentially how much air are we breathing in or breathing out there, okay? Looking at these different, categories. And here are the four of the more common lung volume categories. I would recommend there writing this chart somewhere in your notes and knowing each of these terms here and how you could measure that on a chart. So you will be assessed on taking a look at a chart there. You'll be given one of these, for example, set of arrows there, and you'll have to tell me what does that set of arrows represent. Okay? Let's first look at tidal volume. Okay, tidal volume is represented by this distance here. Okay, so between these smaller red lines, looking at breathing in and out. So tidal volume is the amount of air breathed in or expired per breath. So that's tidal volume represented by TV. Inspiratory reserve volume, or IRV, is represented from this line to this line. So if you were to take the end of tidal inspiration, meaning you breathe the air you would normally breathe in at rest there, or the amount of air that you breathed in there. If you were to try to breathe in any extra air beyond that breath in standpoint, that total amount of air that you could breathe in, okay, would be your inspiratory reserve volume. So how much extra air could you breathe in after you breathed in a normal amount of air? That's considered your inspiratory reserve volume. On the flip side, your expiratory reserve volume is the amount of extra air you could breathe out at the end of a normal breath out during tidal volume. Let me demonstrate using sounds here what an example of inspiratory reserve volume or expiratory reserve volume would be. So example of inspiratory reserve volume, if I breathe in normally and then I breathe extra in, that extra breath in there would be considered your inspiratory reserve volume. Likewise, if I breathe the air out normally and then I breathe extra air out, so that extra amount of air that I breathed out after my normal breath out, that would be considered my expiratory reserve volume. Lastly, we have what's called residual lung volume, meaning if I breathed all the air out I could, what's the extra amount of air that's still remaining in my lungs at that point? And it's important that we have extra air that we can't breathe out in our lungs for this very reason. Okay? If we were to breathe all the air out of our lungs would kind of be like wet shrink wrap. So if you ever you've covered food there with plastic wrap, and if you ever gotten water on that, or you've covered something that is wet, if that shrink wrap there would come together with that wet part in the middle, the shrink wrap just suction cups together. And it's a little bit annoying there to try to pull them apart. Well, likewise, inside your lungs, it's a very hot, humid environment, okay? So it's damp in there. So if your lungs would breathe all the air out that it possibly could there, that lung would just snap together and it would be very difficult to bring that or expand that lung again. It's one reason why if you get a collapsed lung there, you oftentimes have to go in for a medical procedure to get that lung working again, because that that lung is completely collapsed. It's virtually impossible there to pull it back apart again. So there's always got to be a little bit of air remaining in the lungs so it does not collapse completely. In addition to lung volumes, we've also got these things called lung capacities. And again, make sure you have this chart, which is the same as the previous one. Make sure you have this chart down somewhere in your notes, as well as these 4 different terms there, and understand where they are measured here on that chart. Total lung capacity, okay, is the total amount of air that you could have in your lungs after you've breathed in as much as you can. So essentially going from all the way to the top to all the way to the bottom, okay, that would represent total lung capacity. TLC over here on the right. Forced vital capacity, okay, forced vital capacity is the maximum volume that can be of air that can be expired after maximal inspiration there. Okay, in this particular chart there, it's represented by VC. Okay, but forced vital capacity is maximum amount of volume expired after maximal inspiration. So going from here to here, VC in this particular chart is the same thing as FVC, so forced vital capacity. Inspiratory capacity, okay? Inspiratory capacity is the maximum volume inspired following tidal expiration, okay? And this is not represented by arrows here, it's represented by this box right here, inspiratory capacity, going from here all the way up there, okay? So following tidal expiration, okay, breathe the air out normally, the total amount of air from here to here would be considered inspiratory capacity. And then we got functional residual capacity. Okay? This is the total amount of air in the lungs after a tidal expiration. Okay? So FRC there for functional residual capacity. It's represented from this line here all the way down. So again, this slide and this slide Make sure you have these volumes and capacities jotted somewhere in your notes as well as this chart. So with breathing air in and out there, okay, there's kind of a few different things that happen, okay, to help us with breathing air in and out. So during inspiration, okay, breathing air in, the lungs become larger, okay. So lungs become larger, okay, lungs expand there. When the lungs expand there, okay, as the lungs get bigger, okay, the air molecules that are in the lungs there are more spread apart, okay, which will make sense there. Okay, if a chamber is all of a sudden larger than what it normally would be, okay, that means that the molecules would be farther apart there. Okay. Now, when this happens there, as the lungs get bigger, okay, with the same amount of air in there, okay, the air molecules are further apart from each other. Okay, so that means that there is less pressure in the lungs there, okay, less pressure in the lungs, okay, when those lungs have gotten larger there. Okay, and what this does there is because there's less pressure now in the lungs, air wants to go to an area of lower pressure, so air will flow into the lungs. Okay, this assists with inspiration. Now let's take a look at expiration, blowing air out. Okay, lungs deflate, meaning lungs become smaller. As the lungs deflate there and get smaller, the chamber is smaller now, so the molecules of air are closer together. And as they're closer together there, this increases the pressure of the lungs. So a smaller container with the same amount of air in it means pressure is going to increase. So now the pressure inside the lungs is larger compared to the pressure outside of the body. This helps air to go out of the lungs. Here's a visual representation of what's happening there, okay, during inspiration and expiration. During inspiration there, your diaphragm, okay, this muscle on the bottom of your lungs there, contracts and pulls down. Essentially, and this does there is it makes the lungs bigger. And since the lungs are bigger, the pressure inside the lungs is less compared to the pressure on the outside of the body. This assists with air breathing into your lungs. So inspiration there. During expiration, the diaphragm relaxes. When the diaphragm relaxes there, okay, this allows the lungs to go back to their original shape, meaning they're getting smaller. Therefore, now the pressure is higher inside the lungs compared to outside. Therefore, the higher pressure, air wants to go from higher pressure to lower pressure, forcing air out of the lungs. On the right side here, we'll talk about in a little bit here, but as you breathe in, okay, especially during exercise, your rib cage will actually ribs will be pulled up, okay, making the rib cage wider, okay. And when we expire or breathe air out, the rib cage will come back down. And the rib cage going up during inspiration there, okay, is partially due to muscles actually being active, helping pull those ribs up. Okay. Now, at rest there, okay, the muscles at rest, normal breathing there, the muscles that help assist with inspiration or helping breathing air in is going to be the diaphragm. Okay, diaphragm contracts there, help to bring air in, as well as the external intercostal muscles. If you see costal, think ribs. Inter meaning between ribs, okay? So external internal intercostal muscles, those assist with pulling that rib cage up. As we start exercising, more muscles that assist with helping bring that rib cage up are going to be your neck muscles, specifically your scalene muscles and your sternocleidomastoid muscles. In addition there, during maximal exercise, when we reach really fast speeds and trying to run as fast as we can or swim as fast as we can, especially for a longer period of times, your trapezius muscles, okay, big neck muscles there, okay, will also assist with breathing in, as well as some of the extensor muscles of your back and neck. Muscles assisting with expiration or breathing air out at rest, there aren't any muscles that assist with expiration. Okay, taking a look at the slide, okay, at expiration, this diaphragm is relaxing. So it's not contracting during expiration, it is relaxing. So the diaphragm muscle is not doing any work there when it's relaxing during expiration. So at rest there, okay, essentially no muscles are being active, okay, to help expel that air out. Okay. We do know that the lung tissue is stretchy, kind of like a balloon. So just like if you let air out of a balloon, it will, the stuff that makes up the balloon will essentially, like, it'll just relax, helping push that air out. Likewise, the lung tissue there, okay, will just passively recoil there to relieve the stress that's caused by the expiration. However, during exercise, there are some muscles that are active. One is we got some intercostal muscles, but instead of them being external, okay, as during inspiration, our internal intercostal muscles will be active there to help with expiration. Essentially, these muscles are between your ribs, and they help pull the rib cage down, okay, helping push that air out of your lungs. Additionally, you got your abdominal muscles that will contract, helping bring that rib cage down to help expel the air out of your lungs. Now, along with talking about air on the inside of your lungs, okay, becoming either area of higher pressure or lower pressure compared to the outside of the body, we've also got this cavity, okay, called the pleural cavity. And essentially it's this space here, okay, between the outer and inner membranes there, okay, of the lungs. Okay. And essentially what happens is we've got this gap here, okay, as you can see right here and right here. But as you breathe in, okay, there, the rib cage will pull up there, and this gap will become a little bit larger, okay? And when this gap becomes larger there, okay, pressure goes down. So breathing in, this pleural cavity actually becomes more negative, okay, causing air to come in, okay? And then when you breathe the air out, that little cavity there, the little space there, will actually get smaller, bringing the pressure a little bit higher, okay, therefore helping assist with breathing the air out. So due to that, we've got two different ways that pressure changes when we breathe the air in and out. First we got is intrapulmonary pressure, okay? Intra meaning between, pulmonary, okay, referring to the lungs there, okay? And so what intrapulmonary pressure is the difference in pressure in the lungs, okay, compared to outside the body. Okay? When we breathe the air in, okay, the pressure in your lungs there is going to be negative. And so that would make sense. Negative pressure inside your lungs there, okay, therefore helping breathe the air in. As we breathe the air out, it becomes positive intrapulmonary pressure, therefore forcing the air out. Now, intrapleural pressure, okay, in that little cavity there between the pleural cavity and the outside of the body, okay, so this will always be negative. So essentially this gap here, okay, there will always be a negative pressure there. However, okay, during inspiration it becomes more negative, and during expiration it becomes less negative. So still a negative value, but it's closer to zero, okay, during expiration compared to further from zero. So we've been talking about breathing air in and out, and the reason we breathe air in and out is we got to exchange our gases. So how does oxygen and carbon dioxide, how is it exchanged and how is it transported throughout the body? We'll talk about that in the next several slides. So the way gas is exchanged there in the body is due to diffusion. Essentially, diffusion is just a random motion there of different gas particles. As I've alluded to earlier, gases want to go from an area of higher concentration or higher pressure to an area of lower concentration or lower pressure. And since it's the amount of air molecules, it's hard to measure how much there actually is compared to if you want to figure out how much mass a person has. Okay, we oftentimes will use partial pressures as a kind of a synonymous measure there to kind of measure the mass of air. Now, understanding it's not the actual mass of air, okay, but just saying how much pressure is being exerted by the air or by that gas there in that particular area. So we can look at partial pressure of gases in a gas mixture. Okay, so how much carbon dioxide and oxygen we have in a gas mixture. But we can also look at partial pressures of gases in a liquid, for example, the blood. So we carry gases in the blood, okay, and we can look at the partial pressures of those gases, or essentially how much gas we have in the blood there, as well as how much different gases we have in the air. So this diagram here shows an example of how diffusion occurs. Okay, let's take a look here. Okay, we got oxygen in one chamber and oxygen in another chamber here. In the top here, we got the partial pressure of oxygen being 160 millimeters of mercury. Okay, don't need to necessarily have to understand why we use mercury and whatnot there, but essentially, this is just saying we have a lot of oxygen on this side, and then on this side here, we have no oxygen. So if for these oxygen molecules to fuse here across this barrier, okay, these gases always want to go from an area of higher pressure to lower pressure. So high pressure here, because there's a ton of oxygen molecules here, compared to low pressure here. So therefore, oxygen is going to travel, okay, towards this area of lower pressure here. That's what diffusion is happening there. Now let's take a look at another scenario. Same amount of oxygen in the top, but on the bottom we have some oxygen, specifically 80 millimeters of mercury there. Now, what you'll notice here is that, just like before, we got a lot of oxygen going from an area of higher pressure to lower. But diffusion, means that the gases or these gas particles will act randomly. And some of the gas molecules, oxygen molecules, will bump back and go across the membrane the other way. So notice that oxygen travels in both directions across this barrier, but just a lot more of it is coming from the area of higher pressure to lower pressure. In this diagram in C here, notice we got an equal amount of oxygen on each side of the barrier. Okay? Therefore, there's going to be equal movement of oxygen across that barrier, going from bottom to top and top to bottom. If you were to look at the partial pressures of different gases, looking at it in the air that we breathe in on Earth, I don't need you to know the exact percentages here, just get a rough idea of how much these different gases exist there in the air we breathe in and out. So typically, we get roughly around 21% oxygen, less than 1% carbon dioxide, but the vast majority of the air we actually breathe the air in is actually nitrogen. You might think it's oxygen, but it's actually nitrogen is the largest amount of gas we actually breathe in. So roughly 80% nitrogen, roughly 21% oxygen, and less than 1% carbon dioxide. If you were to convert these percentages there to barometric pressure measurements, you could just multiply these percentages by what barometric pressure is, 760 millimeters of mercury there. Multiply those percentages and you would get these mercury values there, for these different gases there in the air we breathe in. Again, I don't need you to know these exact numbers or values. I just need you to get a rough idea of what's going to be the most plentiful gas compared to the gas that's least plentiful. Again, this is the amount that is in the air that we breathe in at rest. Or not at rest there, it's just the amount of air we breathe in. Now let's take a look at how does oxygen and carbon dioxide, how are those gases exchanged in the body? And to set up this diagram, this circle up here, this is going to be your alveoli sac. Again, remember the alveoli sacs is where gases are exchanged. The bottom here is your skeletal muscle. And again, I don't need you to know these specific values of partial pressures of oxygen and carbon dioxide. What I do need you to know is what happens at these different parts there in your body, what happens to the partial pressures. So you notice in the blood in your arteries has a lot of oxygen and has some carbon dioxide as well. So as that blood in the arteries travels to your working muscles, what happens is your working muscles need to do two things. Okay. Number one, they need to absorb oxygen to help keep that aerobic energy system working. In addition, there he has to get rid of the carbon dioxide that's been building up there in the muscle due to the rise in lactic acid. So when we get to the muscle here, notice that the skeletal muscle has a higher amount of carbon dioxide than does the artery carbon dioxide. And likewise, the skeletal muscle has less oxygen compared to the oxygen in the artery. So therefore, through the gas exchange process, through diffusion, some of this oxygen goes to the working muscle, and the working muscle gets rid of some of the carbon dioxide. So that in the veins here, okay, now notice here, in the veins here, our oxygen levels go from 100 to 40. Okay, so essentially oxygen levels are decreasing from the arteries to the veins. And likewise, carbon dioxide levels go from 40 to 46, essentially increasing. So oxygen levels decreasing from arteries to veins, and the carbon dioxide levels rise. And that's due to the exchange of gases there at the skeletal muscle. Now this oxygen low blood, okay, not a whole lot of oxygen, this blood here goes to your alveoli, goes back to your lungs, okay? And again, so higher amounts of carbon dioxide and lower amounts of oxygen. In your alveoli, notice we got high levels of oxygen and relatively lower levels of carbon dioxide. So some of that carbon dioxide is going to be dropped off into your alveoli, so that way you can breathe out the carbon dioxide. And likewise there, the venous blood there will take the oxygen and absorb it, okay? And this blood now, all of a sudden, wham, bam, thank you, ma'am. Now we've got high oxygen blood, low carbon dioxide blood in your arteries, and the process continues. Here's another visual representation of how much oxygen we have in our body and how much carbon dioxide there we have in different tissues in our body, looking at in your capillaries, okay, and specifically the pulmonary capillaries, okay, or the capillaries there in your lungs, and then looking at your tissue capillaries, essentially the capillaries in your actual muscle tissue. So as we get to the lungs there, okay, these pulmonary capillaries, okay, we start with lower levels of oxygen levels rise, okay, and then oxygen-rich blood, okay, goes from your pulmonary capillaries to your arteries. Likewise, carbon dioxide levels start higher, drops off because we get rid of the carbon dioxide going into your alveoli. So carbon dioxide low blood, oxygen-rich blood goes into your arteries. From your arteries, we get to our muscle tissue, okay, and the muscle tissue will absorb some of that carbon dioxide or absorb some of that oxygen, and it will get rid of carbon dioxide. So now in your veins there, we have lower levels of oxygen compared to your arteries, and we'll have higher levels of carbon dioxide compared to your arteries. Now here's the path of what oxygen must travel through and carbon dioxide must travel through, okay, in order to go from your alveoli to your bloodstream, and from your bloodstream there to the working muscles, okay? So taking a look at the alveoli, okay? So the oxygen, okay, goes from the alveolar membrane through some interstitial fluid, okay, through the capillary membrane, into the plasma, and finally into red blood cells. And those red blood cells will carry that oxygen there, okay, to your working muscles. Now, likewise there, okay, carbon dioxide is shifted off, okay, going from your bloodstream, okay, all the way through to your alveoli, and then are expelled in your breaths out there through your lungs. Likewise, at your muscle tissue there, okay, oxygen goes from the red blood cells, okay, into the plasma, capillary membrane, interstitial fluid, into your muscle tissue. So your muscle tissue absorbs that oxygen, and it gets rid of carbon dioxide going from that tissue membrane into your blood. Now, how well do these gases exchange? So how well can we absorb the oxygen, and how well can we get rid of that carbon dioxide? It's due to several different factors, okay? Number one is the partial pressure gradient. Essentially, Okay? If there's a greater difference between the amount of gas in the blood compared to the amount of gas in the tissue or in the alveoli, there's going to be more gas that's exchanged. So, for example, if I go back a couple slides here, okay, notice here in your working muscle there, okay, we got 40 millimeters of mercury of oxygen compared to 100 millimeters of mercury of oxygen in your arteries. So therefore, a lot more oxygen is going to be dropped off in your working muscle there, okay, due to the larger pressure gradient of 60 millimeters of mercury. Compare that to your carbon dioxide levels. So 46 millimeters of mercury of carbon dioxide in your working muscles compared to 40 millimeters of mercury in your arteries there. So only a difference of 6, which means less carbon dioxide will be dropped off, okay? And more oxygen will be consumed going from the arteries to the veins in your working muscles. Number 2 is the length of the diffusion path, okay? So the farther that the oxygen or carbon dioxide has to travel, okay, to go from the alveoli to the capillaries, or going from the capillary to the working muscles and vice versa, the larger that path is, the less gases that will be exchanged. The amount of red blood cells and or hemoglobin concentration, okay, has a big effect on this. So more red blood cells, more hemoglobin that's available there, the more oxygen that can be transported and that can be diffused into the working muscles. The amount of surface area available for diffusion. As I mentioned previously, the amount of surface area in your capillaries is a lot larger compared to your arteries and your veins. And due to that larger surface area, that assists with amount of gas exchange. So apologize for that alarm there. Okay. So the more surface area we have at our capillaries, okay, the larger amounts, or the more more amount of gases that can be exchanged there. And finally, the amount of time spent in the pulmonary and tissue capillaries can affect gas exchange. So if the blood moves slower in your capillaries, okay, that will allow for more oxygen and carbon dioxide to be exchanged compared to moving faster through those blood vessels. So transporting oxygen in your blood, in your body there, okay, there is some oxygen that is actually dissolved there in your blood, okay. Now this amount of dissolved oxygen in your blood only contributes 3 to 4%. So a very small amount of the oxygen that is consumed. Okay? This dissolved oxygen determines the partial pressure of oxygen in the blood, okay, as we showed in that previous slide. Now, oxyhemoglobin is going to play the much larger role in transporting oxygen. Okay? So what oxyhemoglobin is the chemical combination of oxygen with hemoglobin in your red blood cell. Okay? And specifically what hemoglobin is a molecule that contains iron and protein. Okay? And essentially, so this oxyhemoglobin there, okay, this is the main proponent or main factor in transporting oxygen, okay, to other parts of your body through the bloodstream. So instead of oxygen being transported in the blood there, it's mainly transported on these red blood cells. We touched about it a little bit earlier, okay, but partial pressures of oxygen in the active skeletal muscles will be less than normal during exercise, which makes sense because you're exercising, you're using more oxygen, so less oxygen is in your working muscles, specifically below 40 millimeters of mercury. Okay. Now, the same amount of oxygen is picked up in the lungs there during exercise, okay, but more oxygen is going to be delivered to the metabolically active tissues, okay. Meaning, so when I'm active there, okay, any blood that gets to my non-working muscles compared to my working muscles, I'm still going to pick up the same amount of oxygen in the lungs there, okay, but more oxygen will be delivered to those working muscles compared to those non-working muscles there. That's all I got. If you have any questions, let me know. Have a good day.